my name is Lawrence Fu, and today's date is July 4th. So I'll start my present right now. Let me share my screen first. Okay, so good afternoon, everyone. Today, we'll tackle a classic combined spectral problem. We begin with the fundamental information. The molecular formula, C6H14O. First, we calculate the degree of unsaturation, or DU. Using the formula, we find DU equals 0. This is a very important piece of information. It tells us that our molecule is completely saturated, with no double bonds, triple bonds, or ring. The oxygen atom can only exist as either a hydroxyl group, OH, and an alcohol, or as an ether linkage, COC, significantly narrowing down our possibilities. Okay, so for the IR table here, first we locate this critical point and then mark it down in the table. Now let's move on to the infrared IR spectrum. The most prominent feature is the broad absorption peak at 3360 cm, a classic signature for the OH structuring of an alcohol group. This tells us the oxygen is a part of a hydroxyl group, OH. Next, peaks at 2960, 1460, and 1360 confirm the presence of saturated alkyl groups, consistent with our DU equals 0 finding. Finally, the strong CO stretch at the 1160 confirms that we are dealing with an alcohol, effectively ruling out the ether possibility. In summary, the IR spectrum strongly supports the presence of an alcohol functional group on a saturated alkyl skeleton. Next, we analyze the carbon-13 NMR spectrum. We first locate all 5 distinct signals on the diagram. Here are the 5 signals. These diagrams represent different types of carbon atoms. The signal at 65.5 ppm is characteristic of the carbon directly bonded to oxygen, confirming our CH to OH group. The signal at 49.5 ppm is typical for a tertiary carbon, like the center of an isopropyl group. The most interesting signal is at the 23.8 ppm, which has double the intensity. This indicates 2 chemically equivalent carbon atoms, a hallmark of the 2 methyl groups in isopropanol molality. This data confirms the alcohol and isopropyl groups and gives us an account of the different carbon environments. Now, we come to the most informative structures, proton NMR spectrum. Let's break down the data. At 0.8 ppm, a 6H double is the classic fingerprint of an isopropyl groups to methyls. At 1.6 ppm, a 1H setup confirms this is the central CH proton of the isopropyl group. At 1.2 ppm, a 3H doublet is a methyl group attached to the CH group. At 4.05 ppm, a 1H sextet significantly downfilled is the CH proton of the CH to OH group. At 1.3 ppm, a 2H triplet has a CH2 group. Finally, at 4.8 ppm, a broad singlet is the hydroxyl proton OH. The integrals add up to 14 hydrogens, matching our formula, and the splitting patterns allows us to confidently identify 3 key structural fragments. Having identified all the structural fragments, our final step is to assemble them. We have 3 pieces. The first isopropyl groups, CH3, 2, CH. The secondary alcohol unit, CHOH, CH3, and the connecting methylene group, CH2. Counting the carbons, we have 3 plus 2 plus 1, which equals 6, and it matches our formula. The only way to connect these is to place the methylene groups between the isopropanol and the alcohol unit. This gives us the complete structure. CH32, CH, CH2, CHOH, CH3, which is 2-methylpentane, 3O. This structure is consistent with all the spectral data we've analyzed, confirming our deduction is correct. Thank you for listening.